Bismillahirrahmanirrahim. Assalamu alaikum and welcome to this third and final session on control charts. In this session, we'll discuss control charts for defects and defectives, both for constant sample sizes and variable sample sizes. In the context of control charts for defects and defectives, confusion reigns supreme. The confusion lies in discerning whether a given situation warrants monitoring and controlling of defects or defectives. That is, whether a given data set is to be converted into a control chart for defects or defectives. However, there is a silver lining in this confusion, and that is, even if the wrong type of chart is chosen, the results are still strikingly similar. That notwithstanding, I'll try to address this confusion between control charts for defects and defectives. Let us say you are a very successful businessman dealing in fruits, and fruits come to your place in the market or mandi, which is called an arthal, in truckloads. From the farm to the mandi in truckloads. And under consideration are two fruits, watermelon and mangoes. The transportation dynamics of both these fruits are very different. Watermelon, being a sturdy fruit, is just piled into the trucks and transported away. Mangoes, being delicate, are first packed in crates, and then the crates are packed, then stacked in trucks, and they are transported to the market. Let us say 10 truckloads of watermelons and 10 truckloads of mangoes have arrived at the mandi. You, as a successful and very professional businessman, would like to check the quality of these fruits through the process of acceptance sampling. Your acceptance sampling plan for watermelons is that you will pick up a random sample of 10 watermelons from each truck. Any watermelon with more than one defect would be considered defective. The defect could be, watermelon could be overripe, it could be underripe, it could be rotten, it could be broken, cracked, etc. So if there is more than one defect on a watermelon, it would be considered defective. And in this sample of 10 watermelons, if there are more than 2 defective watermelons, then the whole truckload will be discarded. On the other side, obviously you cannot carry out acceptance sampling like the watermelons. What you can do is, instead of 10 watermelons, you can pick up a random sample of 10 crates. 10 crates of mangoes, but not mangoes themselves. Not 10 mangoes, but 10 crates of mangoes. Any mango in any of these crates, you will obviously inspect all the mangoes in these 10 crates. And if there is any mango with more than one defect, that would be considered as defective. Defect could be an underripe mango, overripe ripe mango, or rotten mango, or mango infested with worms, etc. And if there is any crate with more than one defective mango, the crate would be considered defective. And in the whole truckload, if there are more than 2 defective truckloads, the whole truckload will be discarded. as you can see, the data in both cases is very similar, 10, 10, 1, 1, 2, 2. But the context is very different. Here we are talking of direct defects on the watermelons. Direct defects on the watermelons. So essentially, this is a case of defects, and we will use, when we are monitoring and controlling the quality, we'll use control chart of defects. In this case, the focus is not a mango or the mangoes. The focus is crates. The crates are defective. So clearly, this is a situation of defectives, and in order to control quality, we'll prepare a control chart of defectives. Let us see if this situation becomes further clear when we take up this example. On a project site, of course, different building materials arrive, and we are considering two building materials. Huge slabs of marble, very heavy, large in size, and tiny electrical switches which are packed in boxes. These marble slabs, they come singly, vertically stacked on heavy duty trucks. The project manager inspects each slab and rejects any with more than one defect. Defect in marbles could be over crystallization or cracks or wrong sizing, etc., thickness, less thickness. These could be some of the defects of these marble slabs. These electrical switches come in these boxes, and each box carries 100 such switches. The project manager picks up 10 boxes of switches from each pickup load in this case, and inspects each and every switch in those 10 boxes. If a switch has more than one defect, that switch is considered defective. And if a box has more than one defective switch, the whole box is considered defective. And if there's more than one defective box in this sample of 10 boxes, the whole pickup load is rejected. So this situation is very similar to one of mangoes, which we just discussed, and this situation is similar to the one of watermelons. The situation is that 10 trucks loaded with marble slabs and 10 pickups loaded with switches have arrived at the project site. 10 truckloads with marble slabs and 10 pickups loaded with switches are at the marble site. The project manager will inspect each and every marble slab, and he will pick up a random sample of 10 boxes from each random sample of 10 boxes of electrical switches from each pickup, and inspect each and every switch in those 10 boxes. Again, I repeat, if there is more than one defect on a switch, the whole switch will be considered defective. And if there is more than one defective switch in the box will be defective. And if there is more than one box defective, the whole pickup load will be rejected. So this is the situation. When the project manager inspects, he gets this result. These are the number of truckloads, or pickup loads, 10 have arrived. And let's make an assumption that for the time being, the sample size is fixed in both cases. So there are 50 marble slabs on each truck, and there are 50 boxes of electrical switches in each pickup. And let's say when project manager inspects the first truck, he finds 2 marble slabs defective. In the second truck, 1 marble slab defective, and so on and so forth. When he picks up 10 boxes out of 50 from each pickup, he finds 2 boxes defective, 1 box defective, 3 boxes defective, and so on and so forth. I'm deliberately keeping the data identical to make a point subsequently. So case A and case C are cases of fixed sample size. Sample size is 50 in both cases. But there could be a situation where the sample size is different. For example, a truck 1 could be carrying 45 slabs, truck 2 could be carrying 50. And likewise, pickup 1 could be carrying 45 boxes of electrical switches, and pickup 2 could be carrying 50. Whatever the case may be, again, I'm keeping the data identical, again, to make a point subsequently. To start with, we'll take cases A and C. We have so far established that this case is very similar to one of watermelon, so this is of defects. This is very similar to one of mangoes, so this is of defectives. So we are going to take these 2 cases, defect and defectives, both of fixed sample size. We'll deal with the variable sample size later. So let's try to create control charts for these 2 particular cases. Here is the same data. One issue in control charts for defects and defectives is finding out the center line, the baseline, the reference line, or the ideal line around which the performance data would be compared, or around which the performance data would be plotted, and then the graph would be, or the chart would be interpreted if the process, whatever process that is, procurement process or manufacturing process, is under control or not. Let us see if we can find that reference over here. What have we got here? We have got 10 trucks. That is very solid data. Each truck carries 50 marble slabs. Again, a solid set of data. But the most important data is this, which we are monitoring and controlling, and this is the defective slabs. So what is a good reference line, or a good baseline, or a good center line that we can create? Well, 10 trucks and 19 defective slabs. And what immediately comes to our mind is, what is the average number of defective marble slabs per truck, or proportional number of defective slabs per truck? So we have 19 defective slabs and we have 10 trucks. So what is the average number of defective slabs per truck? It is fairly simple. 19 divided by 10, this comes to 1.9. And this figure, this average figure, is referred to as C bar. Because it is an average of 10 trucks, it is referred to with a bar on top. So it is an average, C bar. And the chart which we are going to create based on this data is named after this particular average. This is called a C chart. So if we are happy with the baseline or the center line, which is C bar, that is the average number of defects or defective slabs per truck, then we can see the formula. This is the formula for control limits. C bar, which is this, then Z value, we always take 3. Even if it is not mentioned, we take it to be 3. Why? Because we know that in normal distribution, 99.7% or almost 100% data lies within 3 standard deviations. So we take Z to be 3 and then under root C bar. So we have got all the values. We know what C bar is. We know what Z is. So we can just enter these values and we get an upper control limit of 6.035 and a lower control limit of -2.235. Please remember, we are dealing with discrete data. Discrete data cannot be negative and it cannot be in fractions. So This will be rounded off to a 0 because there isn't anything negative, and this will be rounded off to 6. So the upper control limit is 6 defective slabs. The lower control limit is 0 defective slabs. Can we plot it? Well, we have got the center line. This is the center line. This is the center line, 1.9. We have got the upper control limit. We've got the lower control limit, and we have got the data to be plotted. So we are all set to create the C chart, and this is how it is created. We take the 10 trucks along the x-axis as we have done in the previous charts. This is the upper control limit. I haven't taken the whole number just to make the comparison simple. So 6.035 is the upper control limit, and 0 is the lower control limit. And we plot the defective slabs. In the first truckload, there were 2 defectives. So here we are 2 in the next one, and so on and so forth. And if I can use some animation to show this, this is your samples, number of samples, truckloads. This is your defective slabs in truckload number 1, and so on and so forth. Now moving on to the chart for defectives. Again, a good baseline could be how many defective boxes per pickup, or what is the average number of defective boxes per pickup. So because the data is the same, so it is 19 divided by 10, and we get a figure of 1.9 again. This figure of 1.9 is referred to as NP. For the time being, you can consider NP to be one figure, although they are 2 different. N is the sample size, which is 50 in this case. P bar is something else. But put together, they are NP bar, and this is the value of NP bar in this case. And the control chart is named after this. It is called an NP chart. Okay, if we have found this, we are happy with this, this becomes the reference, this becomes the baseline, this becomes the center line. Excuse me. This becomes the ideal line. Then we can find the formula, and the formula given for such charts is the center line, which is this 1.9, Z, which is 3, center line again, which is this figure here, then 1 minus P bar. And how do we get P bar? Simply dividing NP bar by N and cancel, leaving behind P bar. So if NP is 1.9, we divide it by the sample size, which is 50, and we get that figure. And when we put in these figures into this formula, we get an upper control limit of 5.956, which means 6, and a lower control limit of minus 2.2, which means 0. Now, what is important is the comparison of results. For this, we used a different control chart, and for this we used, a formula, and for this we used a radically different formula. But interestingly, the results are very similar. This is virtually 6. It is as good as this figure. And likewise, this is virtually the same as this one. So that is what I was saying earlier on about the silver lining, that even if we use the wrong type of chart, we still get results which are very close to each other. The difference is negligible. And this is quite apparent in this case also. So because the data is now the same, the control chart, the control limits are virtually the same, the center line is the same, therefore the control chart has to look the same. Both of these charts are drawn on the same vertical scale, and as you can see, the upper limit of both is exactly opposite each other, meaning thereby that these 2 charts are exactly the same, although this is for defectives using a very different formula. This is for defects. Again, a radically different formula, but the results are different. And this plot has to be the same because this data is the same. 19 divided by 10 is the same. So, and these figures are the same. So this data has to be the same. Next, we come to a trickier situation where the data size varies, or where the sample size varies. Here, the number of marble slabs in each truckload is varying, and here the number of boxes containing electrical switches is varying, but I'm keeping the data to the same, again, to make a point. The point is, what is the reference line or the center line in this case? Can we use that simplistic approach again, that is divide 19 by 10? No. Why? Because the sample size is varying. It is 2 out of 45 and 1 out of 50. It is just like two classes. One class has a student strength of 20, the other class has 50. And the first position holders in both classes cannot be compared because one has stood first amongst 20, the other has stood first amongst 50. So obviously, who has stood first amongst 50 has much better performance to boast than the one who has stood first amongst 20. So the same situation here. So how can we then work out a suitable baseline or center line? We still have the 10 trucks and we still have this data. What we can do is now add up all the marble slabs. So 445 is the total of this. So 445 marble slabs have arrived at the site. And amongst these 445, 19 are defective. So if we now divide 19 by 445, we have that baseline, which is the proportional number of defective slabs per truck. And we have got a baseline or center line. Here it is. Proportional defective slabs per truck, 19 divided by 445 is equal to 0.43. And because it is a ratio, it can be expressed as a decimal fraction or as a percentage fraction or 4.3% defectives. This particular average is called U bar, and this chart is named after that. This chart is called the U chart. Again, if we are happy with this choice of ours as the center line, then we can work out a formula, and the formula that is given for limits of this chart is more or less same as the C chart. Instead of C bar, we have a U bar here, but under the root, we divide it by N. Over there, it was simply C bar. Now, with the arrival of N here, which N to take? 45, 50, 40, 42, or what? So that leads to another problem. And the situation is the same on this side. Here, we are going to consider the proportional number of defective boxes per pickup, in which case we'll divide 19 by 445, and the figure we will get is referred to as the P bar, and the chart which is named, the control chart, which will be used in this case, is named after this measurement. It is called a P chart. And this is the formula for P chart. And over here again, we find N figuring in the denominator under the root. So which N to take? 45, 50, 40, or what? So that is the next issue to deal with. Surely, because the sample size is varying, we cannot use a particular sample size, or we cannot use these formulas once for the entire control chart or for the entire 10 data sets or entire 10 samples. So what can be done? The solution lies in applying this formula to each sample. If we do that, then it becomes simple. For example, in this case, n is 45. So we put n 45 here, and of course, the value of u we have already found from the previous slide. So when we do that, we have different upper and lower control limits for each sample. That means our control limits are not going to be straight. They are going to be wiggly. Okay, we have found the center line. We have already discussed that. We are happy with that. U bar on the last slide, 0.043 or 4.3%. We have got the lower control limit. We have got the upper control limit. The final thing left for the chart is what data we are going to plot. Are we going to plot this data as we did for C chart? No, we cannot do that because this is not representative data. This is not proportional data. Because this is proportional over the whole procurement cycle or over all the 10 samples. This is proportional, so it is only logical that we also convert this data into a proportional figure. So in the first truckload, 2 were defective out of 45. So what is the proportional figure? We divide 2 by 45. We divide 1 by 50. We divide 3 by 40. We divide 0 by 42, and this is what we get. And if we have done our calculations correctly, when we add these, it will be exactly the same as U bar over here. That is 0.043. So we have got the center line now. We have got the upper control limit and lower control limits here. And we have got the data to be plotted. So we are all set to plot the control chart. And this is what we do. And as you can see, the control limits are not straight, they are wiggly. But they are mirror image of each other. When the upper control limit dips, the lower control limit rises. When the upper control limit rises, the lower control limit dips. They are mirror image of each other. The x-axis is still the samples over here. This is upper control limit, 0.135. This is lower control limit, minus 0.50, 0.050. And this is the center line, 0.043. This green line. And finally, this data, which is to be plotted 4.4% or 0.044 for the first truck, 0.020 for the second, so on and so forth. And just to show this with a little animation, this is your axis indicating the truckloads or these 10 samples. This is your lower control limit, 0.50 minus 0.050. Then this is your upper control limit, 0.135. And finally, this is your data, not this data, but proportional data, which is plotted here. And this is your U chart. Coming on the other side over here, this column over here is going to be the same because the data is the same. So you will find 0.044, 0.020. But what about this? Well, this has to be different. Why? Because these two formulas are different. These two formulas are entirely different. So you would expect lower control limit and upper control limit of this chart to be entirely or radically different. Well, so you think. Let's see the figures. Lo and behold, they are almost the same as these here. Take the first one, minus 0.050, minus 0.048, virtually the same. Upper control limit, 0.135, 0.133, same. Take this one here, minus 0.051, minus 0.049, 0.136, 0.134. This is the silver lining I was talking about. Even if we get confused between control charts for defects and defectives, we can use either. We can use formula for either and still come to results which are very, very close to each other. No difference at all. Again, let me repeat, look at the formulas, entirely different formulas, but the results are astonishingly similar. Well, if the results are similar, the graphs have to be similar. As you can see, there's hardly any difference between these two charts. Although this is a chart for defects, this is a chart for defectives. Let me now show you this slide again, which indicates that control limits for control chart, for all control charts, is center line plus minus 3 standard deviations. Insofar as control charts for defects and defectives are concerned, the standard deviation is very well defined, but as you saw, each control chart has its own methodology of working out this standard deviation or the formula to work that out. Here is a snapshot of what all we have discussed. All the 4 control charts are displayed, the limits are displayed, the limits and other parameters are displayed on this slide. These are the control charts for defects, and these are the control charts for defectives. The left-hand side is the limits or the parameters of the control chart with fixed sample size, and this is with variable sample size. Same situation over here. In case of defects, if the sample size is fixed, the center line is C bar. If the sample size is variable, the center line is U bar. In case of defects, if the sample size is fixed, the control limits is the center line, this one here, plus 3 and under root of the same. And of course, minus for the lower control limit. If the sample size is variable, the formula is identical, except that the quantity under the root is to divide it by the sample size, which varies with each sample. Therefore, this n being different gives a different value of the upper control limit for every sample. And likewise, the same situation for the lower control limit. In case of defectives, if the sample size is fixed, the center line is NP bar, and in case it is variable, the center line is P bar. The upper control limit is center line, this one here, plus 3, value of Z, and under root center line again, within multiplied by 1 minus P bar. P bar is found by dividing NP bar by N, and cancel, and we are left with P bar. And minus for the lower control limit. When the sample size is variable, then instead of NP bar, we have simply P bar, and the N transfers to the denominator. But because this N is variable for every sample, therefore, the upper and control limit is different for every sample. and of course minus for the lower control. The final thing to remember in these charts is that everything to the right of Z, everything to the right of Z is the standard deviation of that chart. Let me try to draw this. This is the standard deviation of an P chart. Sorry, P bar chart, a P chart. This is the standard deviation of the NP chart. This is the standard deviation of a U chart. And this is the standard deviation of a C chart. On that note, we come to the end of this session and on the to the end of the subject of control charts. Thank you for joining me, and until next time, Allah Hafiz.